Black holes lose mass at a rate of 1 atom every 10 million years. Stephen Hawking's 1974 paper proved this evaporation with quantum field theory. But your body emits more thermal energy in 1 second than a black hole does in a century. Hawking lay in bed in Cambridge, late 1973, determined to disprove a young physicist's radical idea. Instead, he discovered that black holes are slowly dying and proved Jacob Bekenstein right. In 1972, Bekenstein, then a PhD student of John Wheeler at Princeton, had proposed something that seemed absurd. Black holes have entropy. They have a temperature. If they have a temperature, they must emit radiation. To the classical physicists who had built their understanding on Einstein's general relativity, this was not just wrong, it was offensive. A black hole was defined by the no-hair theorem. It had only mass, charge, and spin. It was the perfect cosmic vacuum cleaner. Nothing, not even light, could escape its gravitational grip. The idea that a black hole could radiate, could lose mass, could eventually vanish, that contradicted the very definition of the object. Hawking himself was among the skeptics. He had already made his name in black hole physics. In 1970, working with Roger Penrose, he had proven the second law of black hole mechanics. The total area of a black hole's event horizon can never decrease. It was a beautiful, elegant theorem that paralleled the second law of thermodynamics. But Hawking saw it as an analogy, nothing more. When Bekenstein took that analogy literally and argued that black holes must possess real thermodynamic entropy, Hawking pushed back. He thought Bekenstein had gone too far. The mathematics was elegant, but the physical conclusion was absurd, so Hawking set out to settle the matter. He would use quantum field theory, the mathematics that describes how particles behave in the quantum realm, and apply it to the curved space-time just outside a black hole's event horizon. He expected his calculations to prove Bekenstein wrong. He expected to show that no radiation could escape. Instead, the equations told him something else entirely. The quantum vacuum is not empty. It is a seething foam of virtual particle pairs, particles that pop into existence and annihilate each other in a fraction of a second. Normally, they appear and disappear without leaving a trace. But near a black hole's event horizon, something different happens. The gravitational field is so intense that it can tear the pair apart. One particle falls into the black hole. The other escapes into space. To a distant observer, that escaping particle looks like radiation, coming directly from the black hole. Hawking calculated the spectrum of this radiation. It was thermal. It had a temperature, and that temperature was inversely proportional to the black hole's mass. The implications were staggering. A black hole with the mass of our Sun would have a temperature of a fraction of a degree above absolute zero, far too cold to detect. But a small black hole, say one with the mass of a mountain, would be hot. It would radiate intensely, and as it radiated, it would lose mass. As it lost mass, it would shrink. As it shrank, it would get hotter and hotter. The process would accelerate. In its final moments, the black hole would release a tremendous burst of energy, an explosion. Hawking titled his 1974 paper in the journal Nature with a question mark, "Black Hole Explosions." It was not just a discovery, it was a crisis. For the first time, general relativity and quantum mechanics were forced to confront each other directly, and the result was a paradox. If a black hole evaporates and disappears, what happens to the information about everything that fell in? Quantum mechanics insists that information cannot be destroyed. Hawking's radiation seemed to say it could be. That contradiction would become the black hole information paradox, a problem that has haunted theoretical physics for over 5 decades. But in that moment, lying in bed in Cambridge, Hawking did not yet see the paradox. He saw only the beauty of the mathematics. He later described it simply, "It was a moment of great excitement." The paper landed in the office of Nature editor John Maddox in early 1974. It was barely 2 pages long. The title carried a question mark, "Black Hole Explosions." That punctuation was deliberate. Hawking was certain about the radiation. He was less certain about the final stage, the explosion itself. He had calculated the math, but the physics of a black hole's death throes pushed into territory where even he could not see clearly. The mechanism he described was elegant and devastating. Near the event horizon, the quantum vacuum produces pairs of virtual particles, electrons and positrons, photons and their opposites, all flickering into existence using borrowed energy. Normally, they annihilate within a Planck time, repaying the debt. But at the event horizon, gravity tears them apart. One particle falls inward, carrying negative energy relative to an external observer. That negative energy subtracts from the black hole's mass. The other particle escapes, becoming real. To a distant astronomer, it looks like radiation emerging from the black hole itself. Hawking calculated the spectrum. It was perfectly thermal, a blackbody curve. That meant the black hole had a temperature. He derived the formula. The Hawking temperature equals Planck's constant times the speed of light cubed divided by 8 pi times the Boltzmann constant times the gravitational constant times the mass. The result was astonishingly small for large black holes. A black hole with 3 solar masses, a typical stellar remnant, has a temperature of roughly 6.2 nanokelvin. That is about 6 billionths of a degree above absolute zero. The cosmic microwave background radiation at 2.7 Kelvin is over 400 million times hotter. Such a black hole absorbs far more energy from the universe than it emits. It is not dying, it is growing, fed by the glow of the Big Bang's afterlight. But the formula also carried a dark implication. Temperature is inversely proportional to mass. A smaller black hole is hotter. A black hole with the mass of a mountain, roughly 1 billion tons, would have a temperature of about 120 billion Kelvin. It would glow in gamma rays. It would radiate with the intensity of a nuclear reactor. Losing mass makes it smaller. Smaller means hotter. Hotter means faster radiation. The process accelerates. The black hole does not fade away gently. It races toward its end. Hawking calculated the lifetime. A black hole of 1 solar mass would take 1067 years to evaporate, a number so large it dwarfs the current age of the universe. But a black hole of 1 billion tons would live for only a few billion years. If such primordial black holes formed in the density fluctuations of the early universe, some should be exploding right now, in our own cosmic epoch. Hawking's question mark was asking, can we see them? Can we detect the final gamma-ray burst of a dying black hole? He presented these results at a conference in Oxford in 1974. The room was packed. Dennis Sciama sat in the front row. Roger Penrose was there. So were John Wheeler and Jacob Bekenstein. When Hawking finished speaking, the silence lasted a full 5 seconds. Then the debate erupted. Some physicists refused to accept it. The mathematics, they argued, must contain an error. A black hole could not radiate. It violated everything they knew. Others, including Bekenstein, felt vindicated. The young PhD student who had been dismissed as reckless now saw his hypothesis confirmed and extended. The following year, 1975, Hawking published a second paper in Communications in Mathematical Physics. This one was 22 pages long. It was rigorous, formal, and complete. Titled Particle Creation by Black Holes, it became the canonical reference. In it, Hawking laid out the full derivation using quantum field theory in curved spacetime. He addressed objections. He calculated the exact emission spectrum for scalar fields, electromagnetic fields, and gravitational perturbations. He showed that the radiation was independent of the black hole's internal structure. It depended only on its mass, charge, and angular momentum. The no-hair theorem, it turned out, had a quantum extension. The radiation carried no information about what fell in. That last point would become the seed of a crisis. But in 1975, the physics community was still absorbing the shock of the discovery itself. Hawking had done something unprecedented. He had taken the 2 great pillars of 20th century physics, general relativity and quantum mechanics, and forced them to speak to each other. The result was not a complete theory of quantum gravity. It was something more immediate, a concrete, testable prediction. Black holes are not eternal. They are not black. They glow faintly, and over unimaginable timescales, they dissolve into nothing. The discovery was not the end. It was the beginning of a crisis that would consume theoretical physics for the next half-century. Hawking had shown that black holes radiate. He had shown that they evaporate. But his equations also revealed a terrifying consequence. The radiation was purely thermal. It carried no information about what had fallen in. A black hole formed from collapsing hydrogen would emit the same radiation as one formed from collapsing books, pianos, or people. The information about the original matter, its quantum state, its history, its very identity, appeared to be lost forever. This was not a minor problem. It was a direct violation of unitarity, a foundational principle of quantum mechanics. Unitarity states that the evolution of a quantum system is reversible. Information is never destroyed. It can be scrambled, hidden, or transformed, but it cannot vanish. If a black hole evaporates completely and leaves only thermal radiation, the information is gone. The universe, in effect, forgets. Hawking insisted this was the correct conclusion. Quantum mechanics, he argued, would have to give way. The physics community split. In 1997, Hawking made a bet with Kip Thorne at Caltech and John Preskill, also at Caltech. Hawking and Thorne bet that information was indeed lost in black holes. Preskill bet that it was preserved. The wager was a set of encyclopedias, of the winner's choice. The bet became legendary. It was discussed at conferences, in papers, in late-night arguments at blackboards. It symbolized the deepest tension in modern physics. The conflict between general relativity and quantum mechanics played out at the edge of a black hole. In 2004, Hawking conceded. At the 17th International Conference on General Relativity and Gravitation in Dublin, he walked to the podium and announced that he had been wrong. Information could escape from a black hole. He presented a new calculation using the ADS-CFT correspondence, a duality proposed by Juan Maldacena in 1997 that connected a theory of gravity in a curved space to a quantum field theory on its boundary. Hawking handed Preskill a baseball encyclopedia, but the concession was not universally accepted. Many physicists felt the calculation was incomplete, that it relied on assumptions that had not been proven. The bet was settled. The debate was not. The attempt to resolve the paradox gave birth to a new vision of reality. In the early 1990s, Gerard 't Hooft at Utrecht University and Leonard Susskind at Stanford independently proposed the holographic principle. The idea was radical. All the information contained in a volume of space can be encoded on its boundary. The universe, Susskind argued, might be a hologram, a three-dimensional projection of information stored on a two-dimensional surface. This was not science fiction. It emerged directly from the mathematics of black hole thermodynamics. If the entropy of a black hole is proportional to its surface area, not its volume, then the maximum amount of information that can fit in any region of space is also bounded by its area. The universe has a pixelated structure. Reality has a resolution limit. Hawking himself continued to work on the problem until his final days. In 2018, just weeks before his death, he published a paper titled Black Hole Entropy and Soft Hair with collaborators Malcolm Perry at Cambridge and Andrew Strominger at Harvard. The paper proposed that information could be stored in soft hair, zero-energy particles that linger on the event horizon. These particles, they argued, could encode the quantum state of the matter that fell in. The information was not lost. It was etched into the fabric of the horizon itself, like a message carved into stone. The paper was not a complete solution, but it was a direction. It was Hawking's last word. As of 2026, the information paradox remains unresolved. No experiment has detected Hawking radiation directly. The temperatures involved are far too small for stellar mass black holes, and no primordial black holes have been confirmed. The theory remains a prediction, a mathematical necessity, a cornerstone of quantum gravity research. String theory, loop quantum gravity, and other approaches all must account for Hawking's discovery. It is the test that any candidate theory of quantum gravity must pass. The philosophical weight of the discovery is immense. If information is preserved, then the universe has a memory. Nothing that happens is ever truly erased. Every particle that falls into a black hole leaves a trace, a quantum scar, a ghost in the radiation. The universe is not a machine that forgets, it is a system that records. And if black holes die, then even the most massive objects in the cosmos are temporary. They are not eternal voids. They are slow-burning candles, flickering across timescales that dwarf the age of stars. Hawking showed us that the universe is stranger than we suppose. He showed us that emptiness is not empty, that darkness is not dark, that the end is not the end. The black hole evaporates. The information escapes. The universe remembers. The question that keeps physicists awake at night is not whether Hawking was right, it is whether we will ever be able to prove it.